Special topic TC06 fracture mechanics and fracture of advanced ceramics. My name is Vandellos. I come from Slovakia, from Slovak Academy of Sciences, and I'll be chairing this session. I would prefer if we can keep the timing, so we have 7 talks within nearly 2 hours. So every talk should have a slot of 15 minutes. I would maybe 12 minutes, if we are not finished, I will stand up and just to remind you, and then in 15 minutes we would stop the talk if this is not the case. So without very much more ado, the first talk is given by Vandellos, and it's coming from Safran Ceramics in France. Please, the floor is yours.
Thank you, Mr. Chairman. Good morning, everyone. I'm Vandellos. I work for Safran Ceramics, and I will present you our works with my colleagues about the stress justification of aircraft structures by modeling a 4-point bending test on the bonded wooden oxide-oxide ceramic matrix composite joints. So firstly, just some words about Safran Ceramics, which is a research platform of Safran Group. We develop technologies with ceramic matrix composite materials in order to reduce environmental impact and to increase performance of Safran's projects. So here we have some example. We develop high pressure and low pressure. We develop high pressure and low pressure internal engine parts and also exhaust parts. So here we have some example of exhaust center body with on the left silicon carbide CFC materials used for the exhaust structures, and on the right with oxide CMC. So when we develop and design CMC structures, we use a classical justification approach. So the first step is the analysis of loadings for some mechanical, vibration, and so on. So here we have an example of thermal gradient on the extreme zone of the structure. And then we define and use material and technological representative experimental tests in order to study the behavior of this kind of structure and also the damage mechanisms of materials. And obviously we use correlation with modeling in order to do that. And finally, using all of these results, we are able to validate or review the design of the structure. So in this presentation, we focus on the adhesive joint. So we use for the substrates woven oxide-oxide CMC materials with alumina fibers and aluminum tricks. And for the bond, this is an alumina-based bonding ceramic cement. So why we have chosen to use a 4-point bending test? Because when we look just the deflection of the structure and the thermal gradients on the stiffness zones is due to the axis symmetric geometry of the cone. When we would like to understand the damage mechanisms of the material, and when we look or just justify the good strengths of the structure, we can take a 4-point bending test for material representative experimental tests. So with this test, what kind of damage mechanisms are expected? We have 2 damage mechanisms. The first one is a failure of the CMC substrate, and the second one is the delamination at the CMC bond interface. Okay, so we have performed experimental campaign. Here I just show you one example of test. Firstly, we have in the load displacement curve, we have 3 phases. The first one is an elastic behavior, and then here at 40 Newton we have the first nonlinearity, and finally here we have a sudden drop in load. So when we look the damage mechanism experimentally observed, we can see the failure of the CMC substrate just close to the corner between the bond and the CMC. So obviously we understand why we have a sudden drop in load. But if we use, in order to understand the first nonlinearity here, if we use an elastic model, we can't understand why we have this type of behavior. So we have to have damage mechanisms of the CMC substrate, and this is what we have done So here we have classical damage behavior of the CMC materials under tensile test. So firstly we have elastic behavior, and then we have matrix damages which appear and which involves a nonlinear behavior here. So under the tensile, the normalized strain, we can have damage matrix, and then we have a saturation of this kind of damage, and this is only the yarns which support the loading until they fail. So in order to model this kind of behavior, we use macroscopic damage model for woven oxide CNC, which is Onera damage model developed at Onera in France. This model describes the compliance evolution of the materials as a function of matrix damages and yarn failures. So here we can see an identification of the model using experimental data under tensile test with different orientation of the microstructure of the woven materials. And I don't have the time to describe all the model, but we have, just remember that we have two damage carrier by microstructure orientation. We have DM for the matrix damage and DF for the yarn failure. And these two scalars participated to have compliance under strain. So then we have added this kind of model on the simulation of the 4-point bending test. Not everywhere, exactly, because due to the contact between the metallic roller and the substrate, and in order to make easy the calculation, we have just used here elastic behavior, but otherwise we have just used ODM. I have chosen to use ODM with fiber failure, with a description of fiber failure here, and without fiber failure here. Why? Because we have observed that we are just yarn failure on the corner due to the fact that in the simulation we have obviously symmetric, and this is not the case in the experimental test. So I have just chosen to describe this fiber failure on one side of the sample. And when you do that and you make the simulation, we can have this result. So in the load displacement curve, we are able to describe correctly the nonlinearity in the end of the phase 1. And this is due to the fact that we have activated DM. So we have matrix damages here in the CMC substrate just under the corner with the bond. And also with this model we are able to describe the final failure of the sample. So at the end of the phase 2 we have matrix damages, which is here, this is a larger zone of matrix damages. And also we have the yarn failure here just under the corner. So we don't be able to predict exactly what we have done in the experimental test, but we are able to describe the phenomenon and the damage mechanisms. So we can be satisfied by this result, but not exactly, because we don't know why we don't have delamination before yarn failure. So we have performed other simulation using cohesive elements. So we added cohesive elements between bond and the CMC substrate. We have used cohesive zone model with a bilinear shape in order to describe the delamination at this interface. So we have two physical parameters, the interfacial strength and the fracture toughness. So we have studied the influence of these both interfacial properties on the macroscopic response. The first result is that we have no effect of fracture toughness. The sudden drop is due to the yarn failure into the CMC substrate here. But if we look at the influence of the interfacial strength, we can see two things. The first one is that we have the same behavior when the interfacial strength is higher than 150 MPa. So this is there are the red and the blue curves here. So we have just the failure of the yarn as previously. But we also we can see also that lower the interfacial strength is, higher the maximum load is here. So with the green and the purple curves, we can see that we have a different behavior. So we can have delamination here, and then the yarn failure. The explanation of this kind of mechanisms is due to the fact that when we use in the cohesive zone model a low interfacial strength value, we have a process zone which is larger. The process zone is the length where the cohesive zone model are damaged but not already broken. Okay, so when this process zone is larger, we add softening behavior on the structure, and due to the softening, the stress into the CMC substrate is lower. Okay, so we don't have attained the threshold that we need to have yarn failure. So this is why we have delamination for this value, and then the yarn failure of the CMC substrate. Okay, so now we have we'll understand where we can have delamination and when we can have yarn failure. So we have not predicted, but we'll describe the different damage mechanisms with this kind of test. So we can be satisfied because we have a good correlation between Onera damage model modeling and experimental data, and we have understood the strong influence of the interfacial strength on the macroscopic response. But we can already use this kind of results to design the structure, because we have other problems. The first one is the influence of the geometry of the corner. We know that we have this is an important parameter on the damage mechanisms of adhesive joints. So can we study this influence using, for example, failed fracture mechanics as previously presented by Le Guyon. And also with other geometric specimen or other process in order to manufacture this adhesive joint, we have changed the damage mechanisms, and we have only delamination between the gum and the CMC substrate. So we have also the necessary studies to perform in order to design next the structures as isocentricity. Okay, thank you very much for your attention.
Thank you very much for the good time management too. We can afford 1-2 questions. Okay, if this is not the case, I will not press it further. Thank you very much again.
Okay.
Yeah. So we have please. So excellent. Our next talk will be given by Oji